Bonjour tout le monde. Je vais commencer en français pour vous montrer mon français du Québec, dont je suis très fier malgré notre fort accent. But I'll switch to English because not everybody speaks French, unfortunately. So, thank you for inviting me. My name is Daniel Fortier. I'm a prof of geomorphology at the University of Montreal. I'm also associate professor in civil engineering and geotechnical engineering in 2 other universities. And I've been invited here. I'm really different than you guys. No offense, eh? It's just really different. So I work, I'm a field-based scientist, and I've been invited to present you permafrost. Okay, so yes, like I was saying, I was invited to present you the world of permafrost, if you're not familiar with that. Like I said, I'm a field-based scientist. I work at a totally different scale than most of you. And before I start, I would like to know if we have people here with either geology training, physical geography, geomorphology, geotechnical. No, okay. And I would like to know in the room who works on either analog of frozen ground and permafrost for the... Okay, good, okay. Well, the way I built my talk, the first part will be really qualitative. So it's just to introduce you to permafrost. So you will be lost a little bit at the beginning because there's no equations. And I know that this is your language, but be patient, it will come in the second and third course. But I need really to place the main concepts on permafrost to start with. And do we have American students or American citizens in the room? 1, oh, so 2, okay, yes, okay, interesting. So for you guys, there will be a tariff. So there will be a tariff. So to get the second lecture, you will have to resolve 2 equations. That's going to be the tariff. Okay, so first, just to introduce myself, I'm the director of GeoCreo Lab. This is a lab that is specialized in the northern regions. And so our mission, we study the interaction between biogeosystems, so ecology and the land, from the Pliocene to the Anthropocene. If you're not familiar, Pliocene, we start to study about 2.8 million years ago to the current period and forecasting what's coming with permafrost. So in Canada, permafrost established itself at the end of the Pliocene, just before the beginning of the Pleistocene, the main glaciation. But it was still there. It was there before the Pleistocene. And then we try to understand and we try to project the transient response of northern ecosystems and infrastructure to climate change for northern regions. And here, this is what we do. So most of the research is fundamental research. So I'm a geomorphologist by training, and we do fundamental geomorphology. And I've been trained as a civil engineer, frozen ground engineering. That's where I started my career in Alaska as a prof there. So I am also interested by infrastructure reaction to climate change. We do geomorphology, earth science, geotechnique. So this is something that you will probably like. We work a lot in the laboratory to characterize the properties of permafrost. So I don't like to take my data from the literature. I like to measure stuff in the field, in the lab, and we model as well. So geotechniques, we will measure heat capacity, thermal conductivity, porosity, hydraulic conductivity, etc. Geocryology is the science of permafrost, and also in the field, we do some geophysics, and we work also with biogeochemistry. I'll present that maybe tomorrow. And this is essentially the carbon cycle, which is a big hot topic for permafrost right now, and I would say anywhere. And also ecology. Why do we need to do all that? Well, if you're from France or if you're from Europe, you're familiar with the concept of terroir, right? So it's the land. the properties of the land. So the wine in Bordeaux is different than the wine du Beaujolais, for instance. We have different soil, we have different climate. That's the same for permafrost. Not all permafrost were created equal. It is different, it changes with regions, it changes with climate as well. So we need to study it with various ways, and I'll present what I mean by that. Like I said, I'm a field scientist. When I was hired in Alaska, I remember very well, the dean told me, when you start your research program, think big. The problem, he never said how big should be. So I established 2 transects, one in the east and one that goes across. So we have we study permafrost on a latitudinal transect that crosses 40 degrees of latitude. We start in the Appalachian Mountain in USA. There is some mountain permafrost in the southern part of Quebec. And then we have various sites up to the tip of North America. So it's north of Ellesmere Island, if you're not familiar, this small island we call Ward Hunt Island. So this is my end member for the coldest, the further north that we can find. And in between, we have also other sites. And also we have sites, a longitudinal transect, again from Quebec down to Alaska, that makes 5,600 kilometers, and it's 90 degrees of longitude. Why I wanted to do something like that? This allows me to see various permafrost types, so various types of landforms, various climate, biomes, and it gives me a very good understanding how it's changing, and it's not homogeneous at all. Periglacial geosystem, this is what we'll be talking about. It comprises a solid interface that contains ice most of the time. It is in contact with a cold atmospheric interface, of course, and we have a coastal interface that is frozen during most of the year. So we have sea ice frozen to the land. This geosystem is dominated by freeze-thaw cycles, and it's occurring, of course, in the various components. This is a system, a geosystem that is pretty different, I would say, than other geosystems like temperate or tropical. And it's essentially due to the presence of permafrost and ground ice. The thermal dynamic, as you know, of the planet is strongly influenced by the cryosphere, and this is peculiar to periglacial geosystem. So I study permafrost, but I also study the whole system, so snow, glaciers, lake ice, river ice, sea ice, and permafrost ground ice. So my favorite is definitely permafrost ground ice, but this will have interaction with permafrost. And when permafrost region or permafrost destabilize, then you start to have very widespread topographical changes in the system, and also ecological changes that is related to ground ice melt. Just very quickly, what we observe over the last 20 years along these transects, we, of course, see a warming with unequal amplitude, and it is geographically explicit. So it changes from regions to regions. Northeastern Canada is colder, and its warming is punctuated by cold years, even nowadays. This is essentially due to the atmospheric circulation. So if you go from Quebec and you go up north, you have a low, atmospheric low that is called the Canadian Polar Trough. And this one will move eastward, westward, and it will change the atmospheric circulation. So it brings sometimes more cold air. The west is different. So Alaska, Yukon, Northwest Territories, the warming started like in the 70s, and it's much warmer in this area. So just that we see some pretty interesting changes and differences. Another thing that I will discuss more and that I think you will be interested by that, positive and negative feedback in the system. And this is where I would like to have physics students working on that. And also, other things that we notice, the past climate legacy and the quaternary history have profound effect on the long-term permafrost response to warming. I'll present in the following days more about that. Yes?
How long ago was the quaternary?
Quaternary, you can say it depends on the scales, but in general, let's talk, instead of quaternary, let's use Pleistocene. Start of glaciations, main glaciation across the planet. So the cooling of the, let's say, and we would say something like 2.8 million years old. So from there, everything, so cycles of glaciation, deglaciation, like that, this has a profound impact on the permafrost dynamics. We'll see, for instance, regarding permafrost thickness. So it cannot be explained. For instance, in Russia, you have permafrost that is 1,000 meter thick. It cannot be explained just by the last glaciation, the Wisconsinian. So it is accumulation over glaciation periods. So the structure of the course, today, Introduction to Periglacial Environments and Permafrost, please see it as, I don't know, maybe a National Geographic or BBC documentary. Sit back, relax. I'll present some nice pictures, and I know you have cravings for equations. It will come tomorrow.
I don't.
Okay, so it is important to just introduce some concepts. Tomorrow, we'll discuss about landforms and the physical processes that accompany the development of landform. And we will discuss about permafrost degradation, so the formation of permafrost. And then we'll talk about degradation of permafrost with global warming, which is called thermokarst, for instance. And then part 3, this is where I'm reaching directly to you. We will discuss about physical and numerical modeling of permafrost dynamics. So I said I'm a field scientist, but I do have a lab equipped with a large cold room, 3 meters, and we have several types of permafrost cells. And then we model things that we cannot measure in the field. Okay.
En fait, c'est surtout pour l'enregistrement. Ici, on fait mieux. Peut-être ça passe dans la vidéo et toi, tu peux pas. Vas-y, parle.
OK.
Non, mais là, il y a tout ce qui est atteint.
Les autres, les grands.
Les grands, ils n'ont jamais été allumés. On avait allumé une fois, mais non. Ah, l'autre qui est rouge, il est pas.
Ça fait vibrer. Ça fait vibrer ça. Ça fait vibrer. Faut les éteindre là, ça va. On va les mettre dehors.
Comme ça, je l'ai mis sur net aussi. C'est compliqué, c'est la première fois que ça se fait.
C'est bien.
Bon.
C'est bien là.
Il y a quelque chose qui a disparu là.
Ouais, vas-y.
Tout d'un coup, on n'entend plus le background, c'est je pense
Ah.
que c'est bon.
Bon, c'est bon? OK. Alors, je disais, I was saying, sorry, you make a sign. Sometimes I switch to French, or I can switch to Portuguese, for instance, without knowing. So. Okay, so physical and numerical modeling of permafrost dynamics. Why I'm interested by that? There are some phenomena with the variability of the field that is really difficult to isolate some processes. And there are things also that, especially for permafrost degradation, we arrive on site and it's done. For instance, a landslide. So we can document the landslide, we can characterize the landslide, but we're not there to measure the triggering mechanism when it occurs. So this is why we try to work in the laboratory. So for physical modeling, I collaborate with Université Paris-Saclay. Some of you know these guys, François Cottard, for instance, Emmanuel Léger. We have a group of physical modeling, so maybe we can also extend with some of you guys. University of Ghent in Maya Roustaé in Belgium, Polytechnique in Montreal. We have collaborators from China as well, the State Key Frozen Ground State Key Laboratory. And we have different facilities and we split the job. So I do this part, you do this part, you do this part, because as you know, physical modeling, it takes forever. Just to build a model, understand what it's producing, so that's why we split the job like that. Okay, what is periglacial, just to start? So the original definition, it was frost action operating at the periphery of inlandsis. Inlandsis are large glaciers that covered North America, Europe, etc. It evolved eventually, and it was about landform and processes related to the presence of freeze-thaw cycle and permafrost in non-glaciated zone, of course. A glacier is permanently frozen, and there is this debate in the earth science community, should we call a glacier permafrost? If you do that, then glaciologists, I'm not sure I can walk out of the room if I do something like that. But we agreed that glacier is glacier and permafrost is the land that is not glaciarized. And so it gives periglacial geomorphology, and you have cold region geomorphology that is also related to seasonal frost, permafrost, snow, and azonal processes like hydrology and things like that. Here, you have the zone of periglacial climate on the planet, so 58% of the northern hemisphere, 55 million square kilometers, affected by freeze-thaw cycles. Where do we find that? And this is important. So I know you're not geographers or geomorphologists, but where we are on the planet matters a lot for permafrost dynamics. So here we are at the very tip of North America. This is a small island called Wardent Island. This is the Arctic Ocean. The North Pole is 600 kilometers to the north. So this is my end point, my end member for cold climate. So polar desert are understudied. Let me just show you something. From the tip of Ellesmere, here, to here, there is one geomorphologist studying permafrost. We used to be like 5, 6. So you won't see a lot of paper on polar desert. We have that in Canada. We have some in northern island of Russia and in Antarctica. So North Hemisphere polar desert, we're so few to study that. To go there, it's very complicated. It takes like a week to get there. We have to rent planes. On site, we have to have an helicopter to travel around, or a snow machine if we go in the winter. This is a summer picture. And what is interesting in this area is the total dominance of cold processes. For instance, lake ice. It doesn't melt entirely. You see, this is ice, the white ice like that we have in several areas. It's multi-year lake ice. The sea ice will not melt totally. You have multi-year sea ice. It can have decades old, and I'll show something during the last course. The Arctic ice shelves. This ice hasn't melted, it's sea ice. It hasn't melted for over 1,500 years. This is cold. This is a really cold spot. The snow that you see here, that's the same, doesn't melt over the summer. It will keep itself maybe for 500 years like that. And then you have, of course, the ground ice of the permafrost. So this is a place where the cold dominates totally. Yes?
What is the exact definition of desert in that case? It's the mean temperature
Yeah, when we talk about polar desert, it needs to have a very low temperature, but it's not the main stuff, because you have all the Arctic that has very low temperature, very low precipitation, but the main point, as you can see on the picture, under 5% coverage of vegetation. And we will see that organic matter and vegetation play a major role in permafrost dynamics. So when you don't have that, it reacts totally differently. Geographic distribution. Now we are in the tundra zone. Yes?
Just so maybe in this polar desert, the temperature never goes above zero, or what's the temperature range?
Okay. The mean annual temperature where I work is -18. Okay.
Average over the year.
Yeah, that's the average over the year. So in the winter, we don't know exactly, because the sensors, we have meteorological station, thermistor cables. We don't know exactly the coldest temperature because there is no sensor that goes to that temperature. Maybe we can have a brilliant physics student to develop a new sensor that goes below -55. So you arrive, for instance, in January, and then on the data logger, we'll record the temperature, and then we get nothing, 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 nothing. We're lower than -55. Very interestingly, 2 years ago, it thawed. It went above zero in December. Maybe you heard about that. There was a very warm event, and yeah, so for polar desert, that will be it. In the summer, I would say the temperature will be above and below zero, and sometimes we can reach maybe 7, 8 degrees C. So it's not super cold. We can find that in, European mountains, this kind of temperature. But I'll talk about that also. What is really important is this change above and below zero for ice development. And this is most of the ice, okay, note that for polar desert, most of the ice is formed in summer. Try to find one place on Earth where it happens. It's really typical of polar desert. Why? We need water, liquid water, to form ice. And we need a cold temperature. So in July, we start, snow melt is pretty much done. And temperature will be above zero. So then you don't form any ice. But some days we go below zero, and all the cryospheric element I showed, the perennial snowbanks, the lake ice and all that, will emit some water, and it arrives in the ground, which now is below zero, and it refreezes. So if you look at the ground ice map, circumpolar ground ice map for polar desert, it's totally wrong. It tells you that it's low ice content. And I'll show pictures at the third day. We often have 70% ice per volume, very, very often in the upper part of permafrost. Okay, let's go back to, tundra. Oops, sorry. Tundra. This is very interesting in terms of landscape and periglacial landforms in general. The main difference with polar desert is the vegetation cover. So we will see it creates a very different conditions for active layer, permafrost thickness, and heat exchange. So tundra, with its vegetation, the vegetation is herbaceous, so low vegetation. We don't have trees in the tundra. So the surface aspect make the snow cover very thin in these areas. And it's also a cold permafrost, so Arctic permafrost. Then we arrive in the very large taiga and boreal forest biome that you can see is a major biome. There we have more vegetation. Of course, we have trees, we have more water in the ground, and I would say that the beginning of permafrost in most of taiga areas is a heritage of past climate, and then you have vegetation colonization and tree growth that comes with the warming, not the recent warming, but after the glaciation. So also, I would say permafrost processes are a bit different in this area. So this area is actually very submitted to warming, very sensitive, a lot of reaction in the landscape. For Europeans and North Americans, we have mountain permafrost. We have a lot of mountain permafrost in Canada, but in general, it's not as studied as in Europe. So this is altitudinal permafrost. And we have the very interesting Tibetan plateau. And this is what the Chinese call the third pole of the planet, interestingly. And this is a very special permafrost that is unique. So the precipitation is really, really, really low. You go there in winter, so I have some sites in the Tibetan plateau that I have not shown in the first slide. And you go there and you see a little bit of snow, it sublimates, and solar radiation are at the top, at the peak all the time. So it creates very different conditions, and the vegetation is very like grass, where we don't necessarily found in tundra areas, for instance. Now, circumpolar permafrost distribution. So this is a map of the International Permafrost Association. I see I took the French one. And permafrost is divided, you will see. The permafrost science has so many definitions and concepts. I'm sorry about that. So we divided the permafrost like continuous permafrost, discontinuous permafrost, sporadic permafrost. Some classification that I use will talk about isolated permafrost and relict permafrost. So for continuous permafrost, you need to have more than 90% of the land that is affected by permafrost. So in some areas you have no permafrost in these areas. Then for discontinuous permafrost, we say 50 to 90, 10 to 50 in sporadic permafrost, and less than 10 in isolated permafrost. So basically in isolated permafrost, the land function as non-permafrost areas most of the time. But this is a very, very strange stuff. We have regions of permafrost like that. But I can tell you, if you go from continuous permafrost to discontinuous permafrost, you don't walk on the line like that. So what does it mean? And we say that with global warming, the discontinuous permafrost will move upward. Who's going to show me that? And how are we going to define that? So to evaluate that, we would need to do a lot of geophysics and coring along a large transect to see that. And we're stuck with these definitions. I just want to specify something. We see here that the permafrost regions, all that, is 24% of the northern hemisphere. So it's fairly important. But again, in some of these regions, we have only 50%. So when we make some kind of a model average and stuff like that, permafrost will represent 15%. And this is really important because most of global modelers working on dynamics of permafrost, they use a 24%. And they project how it will change with this, but we only have 15% of coverage of permafrost. And this is a big estimation, again. At the regional scale, permafrost distribution is mostly controlled by air temperature and a little bit with structural geology. I'll come back later. This is with the geothermal heat flux. So here you have another map of the International Permafrost Association, and here you have the mean annual ground temperature. So you can see that it has a very direct fit between these two. This map also presents something in light blue here. This is subsea permafrost. So permafrost, we have it inland, but we also have it under the sea in some areas. And I will present during the last course new studies that we're conducting regarding mechanism of permafrost aggradation. So everywhere, mostly permafrost is degrading, but in some area of the Arctic, it is aggrading, it is forming, and I'll explain how it's formed. An important part also, you have Canada here, you have the permafrost distribution is continentality. So you can see that the ISO lines here go down in central Canada. Here you have Hudson Bay, but Hudson Bay, it's frozen most of the year. And during the winter, there's almost no snow over the ice cover. So it cools really the area. And so you can see that the permafrost regions, yes, go down in latitude in central Canada here. And in yellow, what you have is mountain permafrost, so the Rockies here, the coastal mountain range in BC, Gaspésie, and Newfoundland. And in Canada, we also have a part of subsea permafrost that is also a heritage of the past climate. When the sea level was lower, so when you have glaciation, you develop glaciers, your precipitation falls on these glaciers, and the sea level go down. When the sea level go down, at some areas, it is exposed to air temperature, the sea bottom, and then you can develop permafrost. And at the deglaciation, you have a sea level rise. So you submerge your permafrost, and then it's subsea permafrost. So that's one mechanism. Okay, definition of permafrost. Another problem. So, soil or rock permanently frozen on whatever thickness, that doesn't thaw over a period of minimum 2 years. So it's a thermal phenomena by definition, but in fact it's really a physical phenomena. So we say it's permanently frozen for a minimum of 2 years. Just the definition makes no sense, I think. And if you want, there's a book, textbook that is very nice, I think, to explain permafrost, the periglacial environment by French. Various editions are available. The thermal regime of permafrost, so it's controlled essentially by heat input and heat loss at the surface. And what is important is the mean annual ground surface temperature. The mean annual air temperature is also, of course, important, but it will be modulated by snow cover, let's say, vegetation and water if you want. So it's really the mean annual ground temperature that is important at the surface. And then it's controlled by the geothermal heat flux. And if you go to the literature for that, it's often taken as a constant, but in fact it varies a lot. So if you are, that's why I was mentioning that structural geology is important. If you're in a tectonic actively setting, you can have a fairly large geothermal heat flux going towards the surface. Most of the thermal regime of permafrost is conductive heat transfer, but not only. And we will see in the following courses that heat convection or heat advection is also pretty important. So it's controlled by the thermal properties of materials, so this you know very well, and the thermal gradient, so temperature at the top and at the bottom. So this is why we like to measure various properties. And as you can see, if you're not familiar with these natural material, you can have quite a bit of difference in for instance, the thermal conductivity of material. But I think this, you know it very well. The type of permafrost, there's different classification. Again, something that is weird. So very often it's with area. So like I presented, continuous, discontinuous, and sporadic permafrost. You can have also the type of permafrost latitudinal, so across the latitude, altitudinal, so with elevation. Sometimes people call about terrestrial and subsea permafrost, like I mentioned. Other people work with the timing of permafrost to characterize it, and this is pretty important. We have epigenetic, syngenetic, anti-syngenetic permafrost. So let's start with epigenetic. I'll give some example. Let's say you have a glacier that push a moraine on the terrain. And a moraine is a glacial deposit that is pushed by the glacier moving forward. Or let's say you have a sea transgression on the land and it deposits some clay on the land. And you have a sea regression after. You have this deposit and then it's exposed to atmospheric conditions. And permafrost will abrade. So this is epigenetic permafrost. This is the most common permafrost that we have. Another one is syngenetic permafrost, and this is quite important. I'll show you why later. Syngenetic permafrost is that you have whatever deposit or a rock, and then you have other superficial material that is deposited at the surface or accumulation of organic matter. Let's say aeolian sand that we find very often in cold climate will deposit at the surface. As it's deposited like that, the permafrost, so this is the original, then the surface elevation, the permafrost will rise with the deposition of the material. So, and as the permafrost goes up, the permafrost table goes up, it will of course freeze whatever it encounters. And usually you will have water. So this is a very ice-rich permafrost across the whole stratigraphic column. Epigenetic permafrost, and this afternoon we'll have a very good, interesting talk about cryosuction and all that. Epigenetic permafrost, you will find more ice at depth. So with climate warming, these two types of permafrost react quite differently. One has ice very close to the surface, one has ice more at the bottom. Anti-syngenetic permafrost, it's the opposite of syngenetic. So on planet Earth, sediment will move sometimes. So you can have a landslide. So if you have a landslide, let's say this is the original, you have a landslide, you remove material. You're not at equilibrium with the atmospheric conditions, so permafrost will abrade downward. So that's another type of permafrost. And we can characterize the permafrost by its ice content. So ice-rich permafrost contains ice over its porosity. So this is not normal. Usually we have ground. We have a porosity, we put water, we fill the container, that's it. But, and you will present this afternoon about that, you can have a physical process, and don't ask me to explain the details, cryosuction is really complicated, that you laugh because you're good at it, but it is complicated. So you have, and I'll present that, you have water moving towards the freezing front. And then you can have water or ice in excess of the porosity. We call it excess ice. This is the only geosystem that has something like that. And you imagine that if you have more ice than place to put the water if it melts, it will create very unstable conditions. This water will have to go somewhere. So we'll see that with permafrost degradation. Ice-poor permafrost is either that you have unsaturated ground and it freezes, so you have less ice than the porosity. Or you can have also, for instance, in rock, just in fractures. So you will have essentially ice in the fracture, so it's ice-poor permafrost. And this one is something that I like a lot, probably never heard about that, antegenetic ice. That means that the ice in the permafrost predates permafrost aggradation. How can it be? How can it be? Very simple. It's the burial of ice that exists. For instance, when a glacier retreats, when it melts, there's a lot of meltwater that transport sediment that can cover a part of this glacier. And if you put enough soil over that, it will prevent the melting. I'll show some example of that. And this is not really taken into account right now, but I'll show a slide tomorrow. I would say that more than 50% of Canadian permafrost has buried glacier ice at depth. We call it a delayed deglaciation. So at deglaciation, we melted some of the glaciers, it was buried, and then it stays like that. So this antegenetic ice, it can be with buried glacier ice, buried sea ice, buried lake ice that we have found, and we have this ice that predates the permafrost aggradation. One interesting example that we published last year is glacier ice that is 700,000 years old in Canada. And just make an editorial comment, you have probably seen in the news that permafrost will disappear from the planet in something like 100 years or so. This 700,000 years ice is 4 meters under the current surface of the ground. So can you imagine the number of interglacials you had in 700,000 years? And yet something that is 4 meters under the surface remained intact, or mostly intact. So that's why I was mentioning the heritage of past climate is super important for permafrost dynamics. Oh, sorry, didn't see your raise.
So the 4 meters, is that like a typical length scale, or what are like the length scales in depth you have to go to like evaluate the type of ice content or type of permafrost you have?
At which depth?
Yeah, well, like what size of probe do you need to like quantify what kind of
Okay.
permafrost you have?
Okay, so what we do in the field, we use, for instance, exposures along rivers. You have erosion, then you have a bank that you can observe and you can sample like that. But you have to be lucky to find this. Otherwise, we need to do some coring. So for the high Arctic, we need a portable core drill. And this is something I could present. So we designed ourselves. It's just a modified, if you want, engine with rods and core barrels that we make ourselves. So my lab is just beside, it's in the physics building, and they have their super machine shop. But for them, I'm very vulgar because I arrive, I want a core, and they design stuff for, mass spectrometry and things like that. But we use core like that, and we core and we remove the samples. But it's limited in depth. What we can do, the deepest I've done is 6 meters. Because you have your engine, you're with your student or something else, you have 6 meters of rods with a core barrel, then you fill it when the core is full. You need to pull this, then you have the engine up there at 6 meters, then you have another student, and then you say, you ready? Okay. So it's limited. When we want to go deeper, we need rigs, it's called, so big machines, but this is impossible for the Arctic. We will need a whole plane to bring it there. So when we use rigs, it's usually in villages, Inuit villages that we find a little bit in northern Canada. And then I reach some things like 20, 30 meters. And most of the time, it's not coring, it's destructive drilling. It's pneumatic drilling, we call it air track. That goes down to 30 meters. And then we can stop and install a small corer, take one sample, very small sample, and continue like that. And we use it usually to install thermistor cables to measure the permafrost temperatures. Then, permafrost is much thicker than 30 meters most of the time. Then we go with geophysics. So what we use, ground probing radar, GPR. It is very good for geometry, if you want. Electrical resistivity, tomography, ERT, is very good for phase. So if you have liquid water, the resistivity will be that. If you have salty water in the permafrost, it will be different. If you have just ice, it will be very resistive. So we can have an indirect evaluation of permafrost like that. This is annoying. And we also use microgravimetry. So gravimetry is used in geology to locate ore, so mineral deposit. Microgravimetry, we use it to interpret the large amount of ice that you can have in the permafrost. So it has a different gravimetry than, let's say, sand, frozen sand. If you have pure ice, frozen sand, it will show up. And we also use seismic to go deeper. But you understand that after 30 meters, geophysics sometimes is geomystic, geomagic, you know? There are so many things interfering with the signal, so we don't know exactly. Yeah, okay, so that's for the type of permafrost. Okay, so I'll spend some time on this graph here, the vertical structure of permafrost. So here on the x-axis you have the temperature, and on the y that will be depth. There is no scale, it's not important. So what this red line represents here, this is the record. Let's say we made a borehole, we put a thermistor cable in the ground. We measure temperature. All the coldest temperature of the year will be plotted like that here. In the summer, all the warm temperatures will be plotted like that here. So this is your mean, this is your amplitude of ground surface temperature, and then at depth, same thing, you can know the amplitude of your temperature. At a given point, as you can see, there is no change, annual change. It's due to diffusivity of the material. And then you have no change during the year, and temperature will be warmer, and eventually we cross the zero isotherm. That's the base of permafrost. If you take this line here and you project it upward, this is your mean annual ground surface temperature. So this is what we use to measure climate change. If this point doesn't move, you don't have really an effect on permafrost. It's normal. We have interannual variability. So you have some change in the amplitude and so on, but you need a fairly constant and strong signal to make this point move downward or towards 0 degrees Celsius. And then most of the processes occur in this area. And here, this is what we call it silent permafrost. Doesn't do anything, doesn't change much. But that's the cold content. That's also important. And then we have here the active layer. So I think most of you know, yesterday I saw some posters about that. The active layer is the layer that freezes and thaws annually. And of course, most of geochemical processes will occur in the active layer. Now, the active layer, it is, just as a rule of thumb, it can be up to 7 to 8 meters in sediment. And in rock, it can be much more, like 10 to 20 meters that freezes and thaws due to thermal conductivity of the rock. And it varies, it's variable according to the climate. The thing is that the climate is not constant from year to year. We know that. The weather changes and all that. So you have an inter-annual variability of your local climate. That means that you have a variability of your active layer thickness and temperature. But the permafrost community treats that as a constant. People will ask you, what is the active layer in your area? Oh, okay, 50 centimeters. But it changes from year to year. So that's fundamentally wrong, this thing. But this is the concept we work with, so we're stuck with this. And here, yeah.
Yeah, but this variability compared to the average, what it is, typically, is it, I don't know, 10 centimeter compared to 50 or?
Yeah, it will vary a lot, okay? And it will be for two things. The properties of the material, okay, wherever you are, this will change. And the temperature itself, the climate. So in some areas, from year to year, it can be 20% in the Arctic, where it's thin. So a small change will make it, we'll see that ice play a big role in that also. See, if you have a large ice content, you have a large latent heat content. It creates kind of a buffer to this temperature change. But, and if you go down to the south, you won't see much difference, okay? Because maybe you have 5 meters of active layer, it won't change much. It will change perhaps a little bit the mean annual temperature of the active layer, but not much. Okay, and we can see that there's a fairly good link between the latitude, hence the climate, and the active layer thickness in meters. Out of this map, I can say that this part is wrong. This part here, and northern Greenland, same thing for Russia here, and the tip of Alaska. It presents thinner active layer in polar desert. It's not right, okay? I mentioned that tundra and vegetation is important because of its thermal property. If you remove the vegetation, you expose mineral sediment. The thermal conductivity of mineral sediment, whatever, will be higher than vegetation. So in the polar desert, you have active layers that are thicker than in tundra areas, most of the time. Not always, but most of the time. And also for global modeling, you know, global modelers, they use that kind of map. It is projected as thinner active layer. And look at the region it represents, so very wrong also for modeling. But what can they do, these global modelers? There's so few measurements of active layer thickness in polar desert, they have to use that kind of map. Yeah. In Antarctica, you will have sublimation, okay? And it's interesting also, you have ice formation without liquid water. So it's water vapor that condensate. And then you have also sublimation. In the Arctic, I would say, maybe in polar desert you have that, but otherwise, no, you're vegetated and you have usually humid ground. Okay, now I want to present you something that is what I've been working on for maybe 10 years now. It's the transition zone. It comprises two layers, the intermediate layer and the transient layer. You have two references if you want to know about that. So what are those layers? Most of the permafrost are graded after deglaciation. So it's bare mineral ground. If you have glaciers, you don't have trees in this area. I mean, under the glacier. You melt the glacier, you expose mineral sediment. In most places except polar desert, you will have vegetation colonization. Then you change your thermal properties. If you have vegetation, it dies in winter. Some part will decompose, some part will accumulate. You will accumulate organic matter. Organic matter has a low thermal conductivity. What happens then? You change the thermal property of your active layer, and the top of permafrost, so the boundary between active layer and permafrost here, the top of permafrost will rise, and we call it the intermediate layer. It is a very ice-rich layer full of aggradation ice. Then we have that. We fast forward hundreds of years and thousands of years. So we have interannual climate variability, invariably in any place. You have extreme warm years and extreme cold years. So that's why the active layer concept doesn't work really well. So if you have, for instance, a very warm year, then you will thaw the active layer deeper. Now we're really in a warming trend, but we still have colder years in some areas. So if you follow 1 to 3 years of thawing by 1 to 3 years of cooling, what will happen? The permafrost table will rise up again. And whatever water it encounters while it's rising up, it will freeze it. So the transient layer here is a very ice-rich layer that is the result of this interannual climate variability. And then you have the active layer on top, and very often you have this heritage of vegetation colonization, very ice-rich layer in the intermediate layer.
But at the beginning, what is your reference state, in fact? Because you have an initial table on how do you define the reference state in your model?
The different state?
The reference.
The reference, okay, I'll show you on the next slide. Okay, what is that? What you're looking at are permafrost cores. Okay, so we have 3 different boreholes. You have here, it's the depth axis, and the image is a CT scan. So we use X-rays. You know, medical CT scans, you can go, you have a broken leg, they put the leg in there, then they can image it in 3D and so on. So we use it for permafrost characterization. It works very well for imaging, and industrial CT scan can be used also to extract the various components because they have different density. So we have threshold. We would say, okay, and we work in medical unit, the Hounsfield unit. We say, okay, this sediment is from this and this value, ice will be a different value, etc. So this is what we use. And what you're looking at, when it's clear like that, it's higher density. When it's dark, it's lower density. So what you have here is ice. So when it's dark like that, it's ice. Sometimes it's mixed also with organic matter, which has a very low density as well. So when I was saying that the intermediate layer is important, you have an example here of intermediate layer. Okay, so you have 25 centimeters of almost pure ice. And I think you will appreciate the images here, because what the structure you're seeing in ice, we call it cryostructure. This is how we describe the permafrost. So it's like geologists, they look at the bluff, they see stratification, they describe it like this. This is our language, cryostructure. And you can imagine what is pale here, what is clear colored, is sediment. So what is the ice content of this thing here? It's very close to 90% ice per volume. And the porosity of, this is sand, the porosity of sand will be what? 23%, something like that. So we should not have 90% ice per volume. And yeah, on this one here, what you're seeing on the top, so this is the bottom of the active layer here. And then this is the transient layer. So where the thaw front goes with different years like that. Here it is located in this part. So sometimes you have transient over intermediate layer, but with warming, this will eventually go down, and eventually you get straight in the intermediate layer and you destroy it. When you destroy or melt the intermediate layer, it does not come back. The transient layer will form at various depths. We will always have interannual variability. And Robert will present about, I don't know if you're working at that scale, but what you're seeing here, this ice, is water that is moving by cryosuction towards the freezing front at the time. So you see it disrupt the sediment, it comes up through cracks, and it comes up through sediment as well. And it displays the material as well. So we use cryostructures to identify the transient layer, and just by logic, we know that the next ice rich zone will be intermediate layer. These two layers are quite important for, just finish that, quite important for permafrost response. If you have 90% ice per volume or 80% ice per volume, you have that over 20, 40 centimeters like that, you have quite an amount of latent heat to extract before making the phase change. So this, and it comes back to my editorial comment about buried ice. Why can it stay there at 4.5 meters under the surface over hundreds of thousands of years? This is probably the heritage of intermediate layer and transient layer. So you need to extract all this latent heat before you melt the ice. So you need quite a bit of heat extraction like that. So it offers a buffer to warming. So with some American colleagues from the University of Alaska, we had, it was finished 2 years ago, a big grant to evaluate the transient layer and the intermediate layer across a gradient that crosses all North America. So it started in Alaska and we finished at Warden Island. So now we know where this is the thickest. It's in tundra area. The polar desert don't have much of this. And then in boreal forest, it's destroyed already most of the time. We can still find it, but we know the band where we have this ice-rich zone, so we know this band will be kind of buffered to warming. At the same time, in the Arctic tundra, active layer is shallow, so the ice is near the surface. So everything we see, you know, in big landslides and all that in permafrost areas that are thawing is mostly from Arctic tundra. And no wonder why. You have ice 40 centimeters under the surface. You have, for instance, you know lemmings, these little mouses from the tundra? You have that. You have a polar bear that is really hungry. He digs into the ground to get it. You expose your ice, then you of course you will melt this ice, and then you will trigger all sorts of processes like landslides and so on. I forgot you. No, who had a question? You. Yeah.
I wanted to go back to this cryosuction part. No, the image you were on was good.
Oh, okay, okay.
But
This.
here, you have your permafrost that starts at the bottom, right?
I have what?
The permafrost.
It's all permafrost. It's all frozen.
Intermediate layer.
Intermediate layer is part of the permafrost.
Okay, but why is there liquid?
It's not liquid. This is ice.
It's just different types of ice.
No, it's the same type of ice, but it has a different geometry, if you want.
But then, where is the liquid coming? Because the way I understood it, you said that there is cross-section going up to the top front.
Yeah, so active layer would be over there.
Yeah.
Okay, so for instance, when you have it's two different processes. When you have organic matter accumulation, the active layer will be thinner because you have a poor thermal conductivity, right? So the permafrost table will go up. You follow me?
Yes.
Okay, so when the permafrost table goes up in the active layer, it freezes the water it encounters along its movement. This is this ice-rich zone.
And you're showing this part?
So, okay, let me restart. Let's say this is 1,000 years ago, here. Then it's colonized by vegetation. In fact, the lighter gray is organic matter. It's colonized by vegetation, and it accumulates like this. So this is the original surface, so the permafrost table will be something here. It will go up, and it will freeze the water in the active layer. Then you continue to have sedimentation. It can be aeolian sand, it can be, let's say, riverine sediment, in the floodplain and things like that. Then you accumulate the permafrost up to the surface. Let's say the top of the screen is the surface. Then you have a change in active layer depth or in thawing over the years. So you go here, you thought it's ice. You have water, we agree. Then it refreezes, the next year it thaws, and eventually you get into cold years. The thaw depth, instead of going here, is here. So all the water here turns to ice.
Yes, but this is not cryosuction.
Huh?
This is not cryosuction.
You will have cryosuction and you will have free water that freezes. Because the freezing front, let's say, will start, it's unfrozen in summer, then the freezing front will go down, and the water will go towards the freezing front by cryosuction.
It's coming this afternoon.
No, but the question is because you said, that it was frozen.
Yeah.
So if it's frozen, there is no water.
Yeah.
You were going like this with the water, and I thought it was frozen down. So
No, but not now, but at a point in history, it went, the thaw front went deeper.
Yes.
And then it doesn't stay like that. In cold years, it will go up.
Yes.
The active layer will be thinner, so your permafrost table will rise,
Yes.
and it will, along the way, bring water either this way, this way, this way, where is the freezing front boundary.
I think when you have ice, you also have water, right? Or
Yeah.
You have like mush layers with water and ice.
Yes, both. Yeah.
So this is why you can have cryosuction and something which is already frozen. No?
But I can make you some drawings. Okay, I promise the people from the kitchen that we will stop and we will be there at 12:30. No, you said even before that. So I'm going to just bore you a little bit with some definitions that are important, but you should know most of it already. Frozen contains ice, of course. Unfrozen doesn't contain ice. All right. Cryotic, I don't know if you have used this term before, below 0 degrees Celsius. So it's not because it's below 0 degrees Celsius that it is frozen. Maybe there's no ice, right? Refers to temperature only, regardless of water and ice content. So it was another semantic problem that was corrected by Jerry Brown in the 70s. Non-cryotic, above 0 degrees Celsius. Then we arrive with the strange stuff, cryopeg. But this is super interesting, and I'm sure because you're a physicist, when I present about that, I'm sure you will be really interested. So layer of unfrozen ground doesn't contain ice that is perennially cryotic below 0 degrees Celsius, in which freezing is prevented by freezing point depression due to dissolved solid, let's say salt in the ground. And it may also contain liquid brine pockets. So this has application for planetary science and so on, but why should we have so much salt in the ground? That it prevents water from freezing. How is it possible?
In the rocks, because water is flowing into the rocks.
It can be from weathering of rocks, but there's something. Where do we see you guys?
Heritage from Rocher?
Yes, who said that? Exact. So where do we find a lot of salt? In the sea. So when we have sea, what do we have at the bottom of the seabed? What's deposited? Okay, you guys, I saw you the first day by the beach. You walk in the beach, you get into the water, you have sand, right? That is salty. You continue. You will get what? Finer sediment at one point, and when you go very far, you will get clay. Okay? So how do we get clay on land if it is supposed to be at the bottom of the sea? You need a sea transgression. You need an ocean or a sea that goes over the land. It comes with deglaciation, and it occurs along continents where you had a sea lowering. And then you have regression because you have isostatic uplift. The weight of the glacier will push the continent downward. You remove the ice, the asthenosphere will react, and you have isostatic uplift. When you do that, water goes back where it comes from. But it does not carry all the clay or the salty sediment, especially clay. Clay is really difficult to erode just by, water like that. So you have this clay, and then it's exposed in permafrost areas. Permafrost will degrade in that. Clay will be full of water. So does it make it a fast freezing or slow freezing? Slow, right? You need to extract, change the temperature of this solution, and then you will have a slow freezing. Is clay a good, do we have a good thermal conductivity with clay? No, much less than sand and gravel. So then you have two phenomena that will slow down frost propagation. So if we have slow frost propagation, what does it do to ice formation? Is it fast? Is it slow? Of course, it will be slow. If the freezing front is moving slow, then the ice formation is slow. The freezing front takes time to get down. Then Robert will tell you everything about that this afternoon. That's the perfect moment for ice cryosuction. But also, if you have slow crystal formation, what happens with impurities in water? Push down. So dissolved organic carbon, any kind of salt that you have, will be pushed down in front of the ice crystals, and then you will increase the salinity of your solution at a point where it won't freeze. So you have cryotic stuff down there, no ice, -10, for instance. So you have a soft layer at depth. And this layer can be below the permafrost. And you can have permafrost underneath. Very, very strange phenomena. And I will stop with that. Talik, that's a Russian term. That's another thing with permafrost. We like to bring all sort of vocabulary because we're not as brilliant as physicists that can write equations. So we say, okay, we're going to give those geomorphologists an image or a word that they will recognize, and we will understand each other. So talik is a Russian name. It's a layer, or it's a pocket of perennially unfrozen ground within permafrost. Okay, so it's different than cryopeg. It's above zero. And you can have that in layers, in pockets. So I'll present about that tomorrow. I'll continue. I'm very late. I'll have to change my presentation. Too much talk. But I appreciate that you give some answers and you make some questions during the talk, because I don't know your level in this kind of material. And be there at 12:30 because the cook will talk to me. Thank you.